All right, so we've looked at our solar system and we know what characteristics we need to what we need to be able to explain with our theory of formation. So what are we going to do? We had 4 different characteristics of our solar system that we observed. Remember, the orderly motion, the different types of planets, the existence of asteroids and comets, and even the exceptions to the rules we need to be able to explain. And as you read in your book, they explain some different ideas or some different hypotheses that were proposed but discarded. For instance, the idea of a close encounter, which basically says that the sun's gravity, the sun got close to an object, or an object came close to the sun, and its gravity captured it into an orbit. The problem with this is that you would never observe such an orderly solar system resulting from successive captures of objects. I mean, there's just virtually no possibility that they would all be moving, rotating in the same direction, and the same thing with their planets. There would be much more random motion. So it's kind of nice to think about a theory or a hypothesis that doesn't actually fit into our characteristics and see why before we go on and talk about, well, we think things happened. So what do we think the composition of the solar nebula was? The solar nebula is basically what we think was there before our solar system formed. Nebula is used a lot in astronomy, and it actually refers to anything that has sort of a non-distinct shape. Nebular sort of means, just like a big glob of something. So the solar nebula was a big cloud of dust and gas that existed before our solar system formed. So what do we think this was made of? Was it half hydrogen and helium and then half heavier stuff, or was it more about 98% hydrogen and helium with the other 2% of heavier elements, or was it less hydrogen and helium and more heavy stuff? It turns out that we believe the composition of our solar nebula was about 98% hydrogen and helium and 2% heavier elements. This is sort of a ratio or a percentage that you should start to remember, because it turns out that our universe as we know it right now is basically 98% hydrogen and helium and only 2% of the heavier elements. And so it only stands to reason that the cloud of material that formed our solar system had that same composition. So basically, where does all this stuff come from? And so it might be nice to sort of look at what we call the galactic recycling process. Basically, if we can start anywhere in this, but let's say we have an interstellar cloud of gas. And this cloud of gas, if it's disturbed in some way, perhaps through a shock wave coming from a supernova in some other part of the galaxy or somewhere else, or some other disturbance that causes sort of little pockets of increased density, and then what happens is within that gas cloud, stars begin to form, and then we have star systems. Now, what happens after that is eventually stars go through a whole life cycle, and at the end of their life cycle, they either explode in a very spectacular way, or they sort of release their outer shells in maybe a less spectacular way. And what happens is then that becomes the next cloud of interstellar gas. Within the stars, as they're fusing materials to make their energy, they're actually creating heavier elements. This we have to sort of preview, something we'll learn about at the very end of the class. During the Big Bang, we believe that basically the materials that were formed at the instant of the Big Bang were hydrogen and helium. And it's all the heavier elements that have been formed during fusion inside of stars and during their explosion, and also during their explosions or supernovas. So that is why our solar system and our universe is so heavily concentrated in hydrogen and helium. Here we see a well-known nebula. It's called the Orion Nebula, which is found in the Orion constellation, where we actually have seen and observed stars forming in the clouds of gas. So these whole ideas of clouds forming, stars forming in clouds of gas, it's not just something we thought up, we've actually observed it. You can sort of see the brightness within the clouds of gas within here. So the nebular theory basically says, we have this cloud of gas, just as we sort of talked about in the recycling process. Something causes it to start to collapse under the force of gravity. And as it's doing this, it's actually sort of begins to rotate. There's always going to be some sort of overwhelming motion in a particular direction. And it also will begin to collapse. It actually starts to flatten out as well. So you should already see that there are two things that we've observed about our solar system that we're able to explain now, is sort of the motion in a particular direction, because this cloud of gas is rotating in a certain direction, and the fact that the cloud, as it begins to collapse, starts to flatten. And so now we have a disk of material, and what is going to happen within that disk is the planets are going to begin to form. The temperature at the very center is where the temperature is the highest. This is where the sun is going to form, and around here is where we're going to have the planets form. We've actually seen evidence that stars, as they're forming, do have disks of material around them. In this picture, you see they've blocked out the star, but you see the disk of material around it. And here's another picture as well. So again, this isn't just something that scientists have sort of thought up out of the clear blue. They actually have evidence, observational evidence, to support these ideas. So how did the planets form? Well, the first thing we might try to figure out is, why are the terrestrial planets so different from the Jovian planets, in that the denser material that they're made up of we found closer to the sun? Is it because of gravity? Did the dense objects sort of get pulled in toward the sun? Or was Jupiter scattered those planets inward? Or was it because only dense materials could condense close to the sun? Or what was it, something about the heat near the sun? It turns out that while we might have thought that it was dense materials would sink towards the sun, it's actually not that, but only the dense materials could condense close to the sun. Now we have to make sure we understand what condensation is. Condensation is the formation of a solid or liquid from a cloud of gas. So think about when you have condensation on your glass. That's water that has formed on the outside of your glass out of the air, in the air that surrounds it. So this is actually very important, this idea that what could become solid material that could form the planets, where those different types of materials could form and be solid, is very important in determining why we have terrestrial planets close to the sun, and why we didn't have the Jovian planets at that location. It turns out that, remember, very close to the center of the nebula where the sun was forming, the temperatures were very high, and only materials like rocks and metals are able to condense at that high temperatures. The hydrogen compounds are only able to condense at much colder temperatures, such as what we would find out where we find the Jovian planets. So even though there's not a lot of rocks and metals in the solar nebula, they could be in the solid form in close to where the sun was forming, allowing for the formation of terrestrial planets that are largely only made up of the rocks and metal material. We didn't see any of the hydrogen compounds because they stayed in the gas form in the inner solar system. And so we talk about the frost line. Within the frost line is where we only find solid rocks and metals. We don't have any hydrogen compounds in a solid form within the frost line. Those are only found outside of the frost line. So they only went into forming the planets further out, and that's where we found the Jovian planets. Once you have the little pieces of material, they start to stick together and start to grow up and get bigger and bigger objects, and so we call this process accretion. And at some point the objects become big enough that their own gravity makes them spherical. And so as the accretion process took place, we started off with lots of very small objects orbiting around the sun, but as the material started to stick together, it started to clear out, and instead of having lots of little small objects, we ended up with very few very large objects, and those became our planets. In their beginning formation, we call them planetesimals, sort of to illustrate or to emphasize the fact that they're not in their final form. So why were the Jovian planets able to get so much bigger? Well, think about it. There was more material to make them up, and so they could also include the hydrogen compounds. So the Jovian planets do have rocky and metal-made cores, but then the hydrogen compounds surrounded those or gathered around those. There was a lot more of that material available, and so those planets became very, very large. Now, we still have these things called comets and asteroids. The comets are different from asteroids in that they are actually mostly ices and not rock, and their orbits are much further from the sun. Think about it. The comets are like very small Jovian planets, where the asteroids are actually like very small terrestrial planets, which would actually explain why the asteroids and comets are found at different locations in the solar system. So as we finish this up, notice that we've really been able to explain most of our characteristics of our solar system through this nebular theory. We have explained the orderly motion, the two main categories of planets, and the asteroids and comets. How do we explain the exceptions? Well, the exceptions seem to be probably due to the period of bombardment, which would have been right after the planets had formed, but there was still a lot of debris in our solar system, and this debris would have been impacting our planets, and in some cases could have knocked a planet over on its side, like Uranus, could have actually caused a planet to begin rotating in a different direction because of a great impact. And we also believe that it may be possible that the formation of our own moon was due to a very large impact with a Mars-sized planetesimal early in the history of our solar system.